In 1935, Albert Einstein and Nathan Rosen demonstrated that general relativity permits tunnels through spacetime. But these classical Einstein-Rosen bridges are not traversable. The geometry collapses so rapidly that no matter or information can pass through before the connection severs. In 1988, Michael Morris and Kip Thorne proposed the first mathematical model for a traversable wormhole. To hold the tunnel open, their metric requires the throat of the wormhole to flare outward. This geometric flaring out condition demands a specific counterforce, sustained by what physicists call exotic matter. Exotic matter must possess a negative energy density. This directly violates the weak energy condition, a standard rule governing all known macroscopic physics, which dictates that local energy density measured by any observer must be non-negative. General relativity alone cannot build a traversable wormhole.
The equations demand a completely unobserved hypothetical substance to stabilize the structure. Instead of relying on a macroscopic placeholder like exotic matter, physicists can substitute an established microscopic framework, quantum field theory. Specifically, we apply the Einstein-Euler-Heisenberg framework. This incorporates nonlinear electrodynamics into the equations of general relativity. The Euler-Heisenberg-Lagrangian extends classical Maxwell equations, adding precise quantum correction terms for extreme environments. We focus on the alpha parameter, accounting for one-loop quantum electrodynamics corrections from vacuum polarization when virtual particles interact in strong electromagnetic fields near the throat. Modifying the stress-energy tensor with this quantum parameter naturally generates a repulsive pressure. It effectively mimics exotic matter, reducing the geometric requirement for an unknown substance. The mathematics test exactly how a microscopic quantum vacuum correction scales up to dictate the macroscopic stability of a spacetime tunnel. To measure the stabilization, we start with the 0,0 component of the stress-energy tensor, which calculates the total energy density of the system. The standard classical density is altered by a new term, 2 alpha times the square of the difference between the electric and magnetic fields. We can evaluate the total energy required to build this modified spacetime using the Arnowitz-Dezur-Misner, or ADM mass. This calculates the mass of the wormhole as perceived by an observer located at an infinite spatial distance. This chart plots the ADM mass against internal electric charge. The 3 curves represent fixed values for the quantum correction parameter, alpha. As alpha increases, the curves shift downward, proving the quantum correction strictly reduces the total mass. Quantum vacuum fluctuations provide a repulsive structural influence that directly offsets the massive energy requirement usually needed to sustain a traversable wormhole. With mass reduced, we must test if this correction completely eliminates the weak energy condition violation. This graph maps local energy density and radial pressure against radial distance. At a radius of 1, the throat, the value drops below 0. The weak energy condition remains locally violated despite the corrections. Next, we evaluate the more rigorous strong energy condition, which accounts for both radial and tangential pressures. Following the curves for different alpha values, they remain strictly positive at the throat. The strong energy condition is completely satisfied. The local requirement for hypothetical exotic matter is not eradicated, but it is drastically mitigated. The nonlinear electrodynamic quantum effects carry the structural load necessary to hold the throat open. Satisfying the strong energy condition translates directly into the physical geometry of the wormhole, governed by the metric's shape function. This 2D embedding diagram models the physical geometry of an equatorial slice of the wormhole. Comparing the dashed and solid lines shows the quantum correction actively modifying the spatial curvature, widening the traversable opening at the throat. To prevent an event horizon from forming, physicists apply a non-constant redshift function. This introduces spatial variation into the gravitational potential, allowing it to decay naturally at larger distances. This spatial variation grants the quantum corrections the mathematical flexibility needed to balance the energy-momentum components efficiently across the entire structure. The macroscopic, traversable shape of the spacetime funnel is a direct architectural manifestation of microscopic vacuum polarization. If these stabilized geometries exist, their gravitational fields will interact with background light. By applying the Gauss-Bonnet theorem to the optical metric,
We calculate how a photon deflects as it travels past the wormhole at a specific distance, known as the impact parameter. In the asymptotic limit, the final deflection angle equation resolves into a set of competing mathematical terms. The standard geometric lensing caused by the physical throat curves the light inward, while the classical electromagnetic charge partially offsets this deflection. Plotting deflection angle against impact parameter isolates a third influence, the nonlinear electrodynamic correction. The Euler-Heisenberg correction enters with a negative sign. Driven by quartic invariance, it exerts a distinct defocusing effect on light rays and small impact parameters. This precise quantum defocusing provides an optical fingerprint, separating these wormholes from purely classical spacetime geometry. Modern radio interferometry arrays and upcoming optical survey telescopes possess the resolution required to search for these specific optical signatures. Astronomy already possesses established observations of the sharp lensing rings generated by the extreme gravity of supermassive black holes. Observing outward defocusing during a background star transit signals an entirely different topology, a compact object held open by repulsive pressure, lacking an event horizon. Quantum electrodynamic vacuum fluctuations dictate macroscopic realities. They are structural variables that alter the total mass and pressure of the spacetime they inhabit. Embedding nonlinear electrodynamics into general relativity mathematically stabilizes traversable wormholes. It utilizes established quantum physics to drastically reduce the reliance on fictional exotic matter. The strict boundary where quantum field theory corrects cosmic topology is where the universe's most extreme theoretical structures become physically plausible.